Today on Macaulay Math, we're tying it all together and sketching curves. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 18 on curve sketching. Our goals for today. We're going to analyze and sketch the graph of a function. This lesson brings together many of the skills learned in previous sections. Using intercepts, first and second derivative tests to find relative maximums, minimums, points of inflection, increasing, decreasing functions, and the concavity of given functions is an important exercise to cement these skills or to revisit areas of weakness that need to be reinforced. I've broken up this lesson into multiple videos because this process can take some time, so let's get started. So, no new math for this particular lesson. It's pretty much just bringing together all of the skills that we've learned so far in calculus and using it to sketch the graph of different functions. So, let's go over some of those tools that we have for curve sketching. First, we're going to find x and y intercepts. We're going to talk about symmetry. We're going to look at the domain and range. We're going to talk about continuity and where there are either removable or non-removable discontinuities. We're going to talk about vertical and horizontal asymptotes, differentiability, relative extrema, concavity, points of inflection, and infinite limits and limits at infinity. All of these tools are going to help us sketch graphs, and we're going to follow them 1 through 10 in general. Sometimes we'll skip around if something doesn't apply, or it's a little bit easier to get to an answer if we skip that. But let's take a look. I've got 3 examples of curve sketching, and then I've got one of building a curve based on information. So let's get right to those examples. First example says analyze and sketch the graph of a function. Label all intercepts, relative extrema, and points of inflection and asymptotes. So I'm going to tell you right now that if you are following along with a slide, you might want an additional piece of paper, because I am going to be extending my pages quite a bit in this lesson, and they probably will not fit in the squares. So just keep that in mind as we move forward. So the first thing we're going to want to do is find our x and y intercepts. And we'll start with a y-intercept because that's always easiest to find. And if I plug in 0 for x, that will cross the y-axis. And if I get 0 on top, 0 squared plus 1 is 1. 0 over 1 is 0. And so 0, 0 is a y-intercept. That means it's automatically an x-intercept at 0, 0. And then we have to say, are there any other values for x where it's going to cross the x-axis? And the only way a fraction can be 0 is if the numerator is equal to 0. So since the numerator can only equal 0 when x is equal to 0, the only time it crosses the x and the y axis is going to be there at the origin. The next thing we want to talk about is symmetry. And this thing has symmetry in the origin, and we'll see that a little bit later. The domain of this function is still going to be all real numbers. And we know that because this expression here can never be equal to 0. If x is positive and you square it, plus 1, you're going to have something bigger than 1. And if x is negative and you square it and add 1, you're always going to have something bigger than 1. So this is always going to be positive. And there's no roots and there's no logarithms in this. So we can plug in negative values into this function, and that will work. So the domain is all real numbers. The range, though, not all real numbers, because we do have a horizontal asymptote, and we'll talk about that a little bit later. We want to talk now about increasing and decreasing. So we're going to take the first derivative, just going to take y prime of x. So this is a quotient, so I'm going to need a quotient rule. So I'm going to go ho-de-hi minus hi-de-ho all over ho-ho. So the bottom function is x squared plus 1. And the derivative of the numerator is just 1. And from that, I'm going to subtract, leaving the numerator alone, and multiply that by the derivative of the denominator. So I'm going to bring down that 2, and I'll have 2x, and then the derivative of a constant is always 0. And that will be all over x squared plus 1 quantity squared. All right, so let's simplify this a little bit. I'll have x squared plus 1 minus 2x squared. So this first derivative will be equal to 1 minus x squared all over x squared plus 1 quantity squared. We want to talk about the critical numbers of this function. Again, the denominator is never going to be equal to 0, but the numerator will be equal to 0 when x is either plus or minus 1. So we have critical numbers at x equals plus or minus 1, and those are the only critical numbers for this. So I have the potential to have a relative maximum or minimum at these particular values. So I'm going to grab a number line here, and I'm going to place -1 and +1. So I want to find where this function is increasing or decreasing. So what I'm going to do here is I'm going to plug in a value into this interval here. And so I'm going to pick -10. -10 squared is 100. And so 1 minus 100 is -99. So I've got a negative in the numerator. The denominator is always going to be positive. So when I go negative divided by a positive, I'm going to get a negative. So on this interval, it will be, I will have negative values for the first derivative. Now that means that the function is going to be decreasing over that interval. I'm going to plug in 0. When I plug in 0, I get 0 here. So I'll get 1 minus 0 is going to give me a positive value. The denominator is always positive. So over the interval from -1 to 1, this function is going to be increasing. And then when I plug in, say, +10, again, I'll get positive 100 here. 1 minus positive 100 is going to be -99. All over a positive value means that this interval will be negative from -1 to positive infinity. That means that this function is decreasing until I get to -1, increasing until I get to +1, and then decreasing from that point on. Since there are no values where this function is undefined, we are going to have a relative minimum at -1 comma, and we'll have to figure that out, and a relative maximum at 1 comma, and we'll have to figure out the y value for that. And we know that because this function is decreasing until it gets to -1, and then it's going to start increasing once you get past -1. So I have a relative minimum there at -1, and then this function is increasing from -1 to +1, and then when I get past +1, it starts to decrease again. So I get a function that's got to look like this. So I have a relative maximum at that particular point. So let's figure out the values of these points. When I plug -1 into the original function, when I plug -1 into this function, I'll get -1 into the numerator. -1 squared is +1, so 1 plus 1 is 2. I'll have -1 over 2. That's going to be -1/2. And then when I plug in +1 here, +2 on the bottom, that's going to be +1/2. All right, so now I have my relative maximums. I have my relative minimums. All right, let's find the second derivative, y double prime. So I have this function right here, and I have to take the derivative of that particular function. And so again, I have to use the quotient rule on this thing. So it's Hody high again. Leave the top function alone, x squared plus 1 quantity squared times the derivative of the top function, which is going to be -2x, minus, I take the top function and I leave it alone, so 1 minus x squared, times the derivative of the denominator. Now this is a composition of functions, so I have to use the chain rule on it. So I'll go 2 and then leave what's inside alone, so x squared plus 1, and then I reduce that squared down to a 1. And then I have to multiply by the derivative of what's inside. So the derivative of x squared plus 1 is just 2x. And that's going to be all over x squared plus 1 squared and then squared again. Now when I go to do this one, you'll notice that I have an x plus 1 squared, or x squared plus 1, and an x squared plus 1, and I have 4x squared plus 1's in the bottom. So I can cancel out an x squared plus 1. So I'm going to do that before I simplify. That's going to make my final answer a little bit easier to get to. So if I cancel out an x squared plus 1 here, I'll have just one x squared plus 1 left over times the negative 2x. And then when I cancel out this x squared plus 1 and I go 2 times 2x, I'll have 4x times x minus 1 quantity squared all over. Now, I've taken away one of these x squared plus 1 values. I had 4, so I only have 3 left. So I'm going to go x squared plus 1 now to the third. Okay. Now, we're going to multiply, and I'm going to distribute this negative 2x to these two terms. So negative 2x times x squared will give me negative 2x to the third. And then when I distribute the negative 2x to the 1, I'll have negative 2x. And then the negative 4x distributed to these two terms will be negative 4x plus 4x to the third. And then it will stay all over x squared plus 1 to the third. And so what I'll have left, when I combine my like terms, negative 2x to the third plus 4x to the third will give me 2x to the third. And then negative 2x minus 4x will be negative 6x all over x squared plus 1 to the third. All right, now why did I do this? I did this because the second derivative will find points of inflection and where the function is concave up and concave down. Now that I have that, I am going to find where it's 0. It's never undefined because this expression is always positive, but it can equal to 0. So if I factor this real quick, I'll have 2x times x squared minus 3. So I have values where this function is going to be equal to 0. Y double prime is 0 at x equals 0 and then plus or minus square root of 3. So I just set this equal to 0 and solve for x. Again, I'm going to create a little number line here, and this time I have 3 values. So negative square root of 3, 0, and then square root of 3. And so when I plug in negative 10 into this function here, negative 10 is going to be negative 1,000 times 2, so negative 2,000 plus 60. So I'm still going to be negative. So over this interval, and again, the denominator is always positive. So I'll have a negative here. And so I'm going to pick negative 1. Negative 1 is between negative square root of 3 and 0. So when I plug in 1, I get 1 here, or negative 1. Negative 1 gives me negative 2, and then plus 6 over positive. So I have positive over positive. It's going to be positive here. And then when I plug in positive 1 will give me positive 2, positive 1 will give me negative 6. I'll have negative 4 over a positive number. That's going to give me a negative. And then if I plug in 10, 10 will make this positive 1,000 minus 60. So it's still going to be very much positive in the numerator, positive in the denominator. So it's going to be positive here. So it's going to change from concave down to concave up to concave down to concave up over those intervals. That tells me that I have points of inflection at negative square root of 3, comma, 0, comma, and positive square root of 3, comma. So I have to figure out those values. Since we want the points, we got to go all the way back up to the numerator to figure those out. So when I plug those values in, and you can use a calculator to do it, but I want to keep this short, so I'm just telling you, you need to plug those values into your graphing calculator. Negative square root of 3 over 4, it'll be 0, 0, because we already know that 0, 0 is a point, and it will be positive square root of 3 over 4 when you plug those into your graphing calculators. Now this function is concave down from negative infinity to negative square root of 3, concave up from negative square root of 3 to 0, concave down from 0 to square root of 3, and then concave up again from square root of 3 to positive infinity. All right. So finally, I want to talk about my asymptotes. There are no vertical asymptotes due to the fact that the denominator is never 0. There's never a division by 0. But there is a horizontal asymptote at y equal to 0. Now it's y equal to 0 because the degree of the numerator is smaller than the degree of the denominator. So this expression grows much faster than that expression, and so when you take a big number divided by a number that's multiplied by itself bigger, you're going to eventually get to 0. All right, so I think I have enough to graph this particular function, and so we're going to put the graph on here, and then I'm going to put in some values that I know. I know that I have to have 0, 0 on the x and y axis. And then I also know that I have a relative minimum at -1/2 or -1, and we're going to put it here so that we can see it. And we'll call this -1/2. And then we'll have another one at 1 +1/2. All right. And then let's come back down. We have points of inflection. So we have a point of inflection at -square root of 3, and then -square root of 3 over 4. Now, -square root of 3 over 4, that is a little bit smaller than -1/2. So we're just going to place it in. We're going to put it right there, and we'll say that this is -square root of 3 over 4. And then we'll have a similar one up here at +square root of 3 over 4. And so we'll put -square root of 3 here, +square root of 3 here, and we'll plot those points. And again, our horizontal asymptote is 0, so we're going to hug the x-axis until we get down to here. It's going to shrink, and then we have a relative minimum there. It's increasing from -1 back up to +1, and then it starts decreasing after that, and then we have another point of inflection where it changes its concavity. And so just reviewing all of the things that we went over. 0, 0 is a point. It's decreasing from -infinity to -1, increasing from -1 to +1, and then decreasing from +1 to positive infinity. Our concavity, it's concave down until we get to square root of 3. It's concave up until we get to 0. It's concave down again until we get to square root of 3, and then concave up until we get to infinity. So I'm fairly confident with my graph. And if we go over to Desmos, now this is the graph of the function that I just graphed, and it looks similar to what we came up with. But just to be sure, let me put in -√3. Let me put in -1. Let me put in 0. Let me put in +1. And let me put in +square root of 3. And we can see when we're looking at these values that all of the things that we talked about when we did the graph appear here. It's concave down and until I get to the -square root of 3. It's decreasing until I get to -1. It's concave up from this value until I get to 0. It's increasing from -1 to +1. It starts to be concave down until I get to square root of 3, and then it's concave up through infinity. So I'm very confident in my graph. I'm going to stop this video here. I'm going to place the other 3 examples together with additional videos, and you can watch them at your leisure.